Most agent bugs are just bad tool args, generate schemas from types, and validate every call. You will learn how to turn Python types into strict schemas, so your agent stops feeding broken inputs to tools, and so you can tell exactly why a call failed. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Agents call tools often. They build arguments and hand them off. When those arguments are wrong, the tool fails silently or throws messy errors. That slows development and hides root causes. Pydantic tool schemas for function calling helps by turning your typed Python interfaces into precise, machine-readable contracts. The model or agent can then see what shape every call needs, and you can validate before you execute. The basic idea is simple. Define a model that describes the inputs you expect. Emit a JSON schema that an agent or caller can follow. At runtime, validate the actual arguments against that schema and return a small, actionable error when something is off. Strengths are clarity and early failure. A downside is one more validation step, but that trade-off often avoids far more costly debugging later. We will build a small toy flow that shows this end to end. You will see how to declare a strict model, get a schema out, validate bad inputs, use those validated inputs in a small retrieval example, and then convert everything into a function calling schema that surfaces fixable errors. This snippet uses Pydantic v2 to define a strict model and emit JSON schema. In simple terms, it shows a model with typed fields and a configuration that refuses coercion. The key idea is that the model declares exact fields and types, then asks Pydantic to produce a JSON schema representation. The important lines are the model definition with concrete types, the strict mode flag that prevents silent conversions, and the call that exports JSON schema. If you change strict to permissive, the schema will still describe the shape, but runtime checks would be weaker, and some wrong inputs could pass. This file gives you the formal contract the agent will follow. Now we will check what happens when the agent sends the wrong arguments. This example validates bad args with Pydantic and extracts a concise error. It shows a simulated bad call, where an argument has the wrong type or a missing field. The code first tries to construct the model from the provided dictionary, and when Pydantic raises a validation error, the example captures it and formats a short, human-readable message. The important parts are the try block that attempts model creation, the exception handling that pulls out the first failing field, and the formatted error string that reports which field is wrong and why. Making the error message shorter helps an agent to produce a corrective action rather than a wall of tracebacks. Next, we will use validated inputs to rank documents by simple matching. This code validates args with Pydantic, then ranks docs by query matches. After input validation, the snippet converts the query string into a simple normalized token set and compares it to token sets for a small corpus. The flow goes validation, normalize query, compute a basic match score per document, then sort by that score. Key lines include the validated query access, the tokenization or lowercasing step, and the loop that counts overlap between query tokens and document tokens. If you change the scoring to require more overlap, results become stricter and fewer documents surface. This example keeps the corpus small so you can see how validation protects the pipeline from malformed queries and from empty strings. Next, we will lock down types so nothing gets coerced unexpectedly. This snippet enables strict typing in Pydantic to prevent silent coercions. It demonstrates configuring Pydantic v2 to reject values that would otherwise be converted, like a numeric string becoming an integer. The core idea is to set strict types at the model or field level, and to show a case where a string that looks like a number is still rejected. The important lines show the strict type declaration, the model instantiation that would have accepted the value in permissive mode, and the validation error that now appears. Tightening strictness makes bugs fail early, but requires that callers produce correctly typed values. So there is a balance between developer ergonomics and runtime safety. Next, we will gather everything into a function calling schema and surface fixable errors to the agent. This example builds a Pydantic-based function calling schema and surfaces fixable errors. It shows how to package a model description, usage hints, and the JSON schema into a single function metadata object that an agent can read when it decides which tool to call. The snippet then demonstrates a failed call, captures the validation error, and converts that into a short corrective message the agent can use to retry. The key pieces are the model to schema conversion, the metadata that describes required fields, and the error to feedback translation that recommends exactly which field to fix. This pattern makes it easy for an agent to self-correct without human intervention. If you map this toy flow to a real service, you would generate schemas for each tool endpoint, include them in tool registry metadata, and log the validation failure types. That lets you count common mistakes and prioritize either schema changes or agent prompting fixes. Recap: it is a way to derive strict machine-readable contracts from Python types and validate every tool call. Use it when agents or automated callers build complex arguments and you want early, actionable failures. One caveat is that strict validation can require callers to be precise, so plan for clear error feedback or slower iteration during initial integration. Next step: measure and scale this approach by adding an error metric and logging for a larger corpus of calls. Then track how validation reduces overall failure rate. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.